Hi, today we're going to start Unit 2. This unit covers transformations, systems of equations, and systems of inequalities, and absolute value equations and absolute value functions. So if you could just put your name on the front cover of your book and your block, and then turn to page 1. So the first concept we're going to cover is function transformations, which you did a worksheet yesterday that had you explore these transformations. So some of this should seem familiar. Before we move on to higher degree functions, we're going to take a closer look at quadratic functions. Since you studied quadratics for the majority of Math 2, you should know quite a bit about quadratic functions, and you might be sitting there thinking, I really don't know anything about quadratics, but you probably remember more than you realize. So we're going to take a look at quadratics. The parent function, well, every function has a parent function. The parent function is the most basic form of any function. So the parent function for a quadratic is just y equals x squared. So that's kind of the simplest quadratic that you can draw, and that one is graphed right here. So if you think about what numbers you could plug in for x and what answers you'd get for y, if you plugged in 0 for x, 0 squared equals 0. If you plug in 1 for x, 1 squared equals 1. If you plug in 2 for x, 2 squared equals 4. And then we have points in the opposite direction. If we plug -1 in, you would have -1 squared. -1 times -1 is +1. -2 times -2 is +4. And this would continue upward forever. In standard form, the way you learned to write a quadratic is ax squared plus bx plus c. And some things that you may remember is that if a is positive, the graph opens upward. And if a is negative, the graph would open downward. So it would reflect over the x-axis. Our c value is our y-intercept. So in this equation, y equals x squared, since it doesn't say anything at the end, it's like having +0, and that's why our y-intercept is at 0. So we started to explore transformational form yesterday, and when you're talking about a quadratic, it's usually referred to as vertex form because a quadratic has a vertex. And other functions that we study don't necessarily have a vertex. So for those functions, we call the same format transformational form. For a quadratic, it would look like this. A times x minus h squared plus k. Now, the a value over here does tell you a lot about your graph. It tells you all the same things that a told you in standard form. So if a is negative, it's going to reflect over the x-axis, so the graph would open downward. Another thing that a does is called vertical stretch and vertical compression. In this course, we are not going to study horizontal stretch and compression. So if you want to envision a vertical stretch, imagine that someone held onto this point and this point on the parabola. They held the two arrows and they pulled upward. If they pulled up, then this parabola would get skinnier. These two arrows would get closer together. A vertical compression means if you pushed down on the arrows. So if you pushed down on them, the whole entire parabola would get wider. H tells you if the graph is shifting left and right, and K tells you if it's shifting up and down. We'll talk a little bit more about this. H is being subtracted. So you may have noticed yesterday that H, if you see x minus 7, then H is really positive 7. And if H was negative 7, you would see x plus 7. So we'll talk a little bit more about that in a minute. There are certain transformations that are evident in standard form. For example, describe the transformation from y equals x squared to y equals negative x squared. The only transformation there is that it would go from pointing upward to downward. We call that a reflection over the x-axis. And in number 2, if we start with y equals x squared, this graph, and we just say x squared plus 3, then what would happen? Well, we know our y-intercept would then be here. So this whole entire graph would shift up 3. Like that. So you can just write up 3. You could write shift up 3, translate upward 3 units. They all mean the same thing. Okay, so that's about all we can tell from standard form. So vertex form is much more useful in describing transformations. Take a look at how the changing values of A, H, and K transform a function. So you are welcome to type in this website and play with this, this website on your own. But you did use one on Desmos last week when Ms. Hunt was here. You had used a similar website. Over here on the right side, you see that we're graphing the function f of x equals a times x minus h squared plus k. And the parent function is shown right now, f of x equals 1 times x squared. So we wouldn't write the 1 necessarily. But if we change the value of a, and we make a bigger than 1, that's going to be that vertical stretch where you're pulling up on the ends of the parabola. So if we pull upward, the parabola gets skinnier. And if we then push downward, if we push down, the parabola gets wider. So as we decrease the values of a, now we're back to the parent function. So anything above 1 is going to stretch the parabola and make it skinnier. Go back to the parent function right here. A compression is anytime you decrease the a value. So if we start at 1 and decrease that, we're looking at decimals, 0.9, 0.8, 0.7, 0.6, 0.5, and so on, until we get to 0. If a equals 0, there is no quadratic because 0 times x squared is equal to 0. So it's just a flat line. It becomes a constant. So a compression is anywhere between 0 and 1. It's all of these, but they have to be bigger than 0 or else it flattens out. Then we go negative. Negative 1, I'm going to just start at negative 1, is the compression, is the reflection of the parent function. So anything that is further away from negative 1, so basically the absolute value of the number is bigger than 1, like the absolute value of 2 is 2, but the absolute value of negative 2 is also 2. As long as the absolute value is greater than 1, this would be a stretch vertically again, but now it's being stretched from below. It's being pulled from below. So if you put your fingers on these ends right here and pulled downward, then it would get skinnier. So that's still a stretch, and compression is still going to be closer to 0. So between negative 1 and 0, now instead of a compression pushing down from above, now it's pushing up from below. So that's a compression, and then it's flat. So that's how A works. And again, I think I pointed out that as soon as A becomes negative, it's a reflection. So as soon as that happened, this whole thing reflected. Okay, H. So if you can look and see the values of H here, when H is 0, if we increase it and we move, the numbers are getting bigger, H is moving to the right. But right now, H is at positive 5. I moved this slider to positive 5. So we moved right 5. A good focal point is we were at the origin, and now we're at 5 on the x-axis. But if you look at the equation, it says x minus 5 squared. That's because h is being subtracted, so it's x minus positive 5. So it would say x minus 5 squared. So when h is positive, it's moving to the right. Let's go back to 0. And now, if h is negative, we would move to the left. So if we stop at negative 5, think about what would happen here. We can see that starting at the origin, if we move left 5, we end up right here. But in the equation, when you plug in x minus negative 5, it becomes x plus 5. So this is what we would see in the equation. When h moves to the left and h is negative 5, the equation will say x plus 5. So h is a little bit tricky. K is not tricky. K is pretty easy. If we increase the values of k, the parabola moves upward. So if we put k at 5, the vertex went from the origin and just went straight up 5. And at the end of the equation, you'll see plus 5. Positive 5, if you plug it in for k, it's just going to be plus positive 5. When k decreases, it moves back downward. And then if we go negative, let's say we go to negative 2. Okay, it's not letting me stop exactly at negative 2. Okay, we'll have to leave it at negative 2.1. But at negative 2.1, if you plug that in for k, it's plus negative 2.1. You would just see minus 2.1. So if you see a negative number at the very end, that means it went down. If you see a positive number at the end, it means it shifted upward. So if we take a look at a function, imagine if a is 3, h is 2, and k is 1, what that would look like. A is 3, h is 2, and k is 1. Okay. So our origin is the focal point. I always start with that. So the origin moved right 2 and up 1. So this shows us right 2 because x minus positive 2 and then up 1. The vertical stretch of 3, you won't really be expected to be able to look at a graph and know exactly what the stretch was, but you may just be asked from the equation if there was a stretch or compression. But if you notice before for the parent function, we had a point at 0 and at 1, 1. Now our first point is at 1. From this vertex, we would go right 1 up 3, and that's because of that stretch of 3. So that's how that works. Again, you're welcome to go to that website and try that on your own. So I want you to try to fill in the blanks here based on what we talked about, and I will fill them in if you wanted to just follow along. A stretches the graph vertically. As A increases, that is actually called a stretch. The graph gets, most students say that it gets narrower or skinnier. So however you want to describe what you saw. And this is when the absolute value of A is greater than 1. So again, I mentioned if a was -2, it would be a stretch because the absolute value of -2 is +2, and that's greater than 1. So as long as it's more than 1 unit from 0, it is a stretch. As a decreases, we actually call that a compression. The graph gets wider, and this is true when the absolute value of a is in between 0 and 1. So we write 0 is less than the absolute value of a, which is less than 1. And basically, that's all your decimals between 0 and 1 or fractions between 0 and 1. This one's pretty easy. If a is negative, the parabola will reflect over the x-axis. H shifts the graph. H is a shift right or left, and it does shift the graph right when H is positive, or left when H is negative. But this is the tricky one. It looks opposite in the equation because of the subtraction. So this was supposed to be, I know it doesn't look like an exclamation point in your notes, but alert. H is the tricky one. H is always the opposite sign of what we see in the equation. Because it's being subtracted. So that's the tricky one. K shifts the graph up when K is positive or down when K is negative. So I'd like you to take a moment. You can pause the video and work through these 3 problems at the bottom to describe each transformation and finish filling in the boxes if you're not, or filling in the blanks if you're not finished. So these are the correct transformations, but I do want to explain that the tricky ones, this was right 4, and that's because we see -4, so H is actually equal to +4, and K is equal to +2. So this is basically like saying X minus whatever H is +4. This doesn't have an H value, so essentially it's like saying -6 times X minus 0 squared and then -3, because X minus 0 would just be X, and you would end up not having parentheses. When we say a stretch of 6, I want you to kind of have an understanding of what that means. It's basically a force that's pulling upward on this function, and the force is 6 times as strong as the force acting on the parent function. So it's a stronger force. If the force was 2, the force would be double the amount of force pulling on the parent function. So when we have a decimal, we say it's compressed by 0.25. That decreases the force on the parent function, kind of like gravity. So it's like a push or pull downward, like a push from above or a pull from below. And that is at 0.25, which means it's only 25% as strong as the force on the parent function. And then this moves left 3. I know that because I see plus 3, so it's really x minus negative 3 squared. And that would become minus negative would become plus. So h equals negative 3 in this case. All right. So we're going to go to the next page. And interpreting vertex form. So given y equals 3 times x minus 4 squared minus 2, find the vertex axis of symmetry, the max or min, and the domain and range. So for the vertex is always just whatever h comma k is. And so the first thing you want to do is look at your function and just figure out what your values of a, h, and k are. In this function, a equals 3. H equals, this is the tricky one, it's opposite of what we see. So it's positive 4. And K equals negative 2. That's not your bell, by the way. So those are our values. So the vertex is pretty simple. It's just 4, negative 2. So these values represent a bunch of different things, which is, again, why vertex form is so much more useful than standard form. If you remember, and you might not, but in standard form, when you had to find the axis of symmetry or the vertex, it was quite a bit of work. You had to use an equation to find the axis of symmetry. So if this were your parabola, the axis of symmetry is the vertical line that cuts the parabola in half. And so I'm just kind of drawing an XY axis. So in this case, it looks like maybe the axis of symmetry is at negative 1. But to find that, you used to have to do, I'm going to say this is the old way, math 2, x equals negative b over 2a. And then if you wanted to find the vertex, you had to use that x value because this point would have the same x value. And then plug that back into the equation and solve for y. So it was a lot of work. But here, if we know that the vertex is on the axis of symmetry, then they're going to share this x value. So this x value matches the vertex x value. So it's pretty simple. It's just x equals 4. And you have to write x equals because it's a line. So an entire line vertically has to start with x equals. Well, if we were to summarize, and I would write this summary because this is what you want to study for your test. The first thing that the vertex form tells us pretty quickly is that the vertex is just HK. We see now the second thing that this tells us is that the axis of symmetry is at x equals, and it's going to be whatever the h value is. So x equals h. A max or a min, you may recall what these words mean. It just means the vertex is the maximum point or the highest point, or the vertex is the lowest point. And where is that value? So max and min is talking about height, high and low. So it's talking about your y value. So for this particular graph, our a value is 3. We need to know that because if a is positive, the graph opens upward and has a min. If a equals a negative, the parabola will open downward, and then it would be a max. So it's just the sign of a. In this case, a is positive 3. If a is positive, that means our vertex is our lowest point. So it's only going to be one or the other. And all you're going to write is that we have a min at what is the lowest point? It would be at -2. So this particular parabola would have 4, -2, and would open upward. So it's a min at the lowest point, which would be -2. For the domain, every quadratic, this is pretty easy, every quadratic function can go left and right forever. So it's a domain of -infinity to +infinity. But we're going to learn other functions, and they don't all have a domain of -infinity to infinity. But all quadratics do. The range goes from how low to how high this goes. So the lowest point is at -2, and then we see this goes up forever. So how low is -2, and the -2 is included, and then it goes up forever. So it's -2 to infinity. So let's finish this summary. We have max or min. It's a max if A equals a negative, then it's a max at what value? It's going to be whatever the K value is, or it's a min if A equals positive. We would say we have a min at K. So it's only one of these. Our domain for a quadratic function is -infinity to +infinity. And we'll discuss different domains when we get to those functions. For range, this one can change if the direction changes. So A has an impact on our range. So if A was positive and we have a min, like the one we have here, then since it's a min, then K is your lowest point and it goes up forever. But if we had a negative A value, K would be our maximum, so the graph would point downward and it would go to -infinity. So let's summarize that again. If A is a negative, your range is going to be starting at K. That's going to be your highest point, and it's going to go down forever. And this is really written backwards, so it should be written least to greatest, but I'm going to fix it, but you can write it next to it as long as you know that they mean the same thing. So it technically should be written least to greatest, but if you wrote it as K to -infinity, I would totally understand what you meant. So -infinity to K, and then if A is a positive, the graph opens upward, so K is the lowest point. So it would go from K up forever to +infinity. So this summary is definitely something you want to study for your next test. And you can use that right now to answer the questions below. You can pause the video, or you can work along with me. Okay, intervals of increase and decrease. are the last page that we need to go over. If you had any questions on the page before, you are welcome to raise your hand and ask questions. And if Mr. Cook needs to come get me next door and bring me over there, that's fine too. So let me know. Intervals of increase and decrease. I think by saying increase and decrease, it kind of implies increasing that the graph would be going up and decreasing that the graph would be going down. So if you look at these equations and you think, like, what could they mean by interval of increase and decrease? When is it going up? When is it going down? So it's kind of implied that if you're saying increase, the graph is going up, that means that the y value is increasing, because that's what gives the graph height. So by saying increase and decrease, we're talking about a change in the y values. And so I'm not asking you about the y values. I'm telling you I want to know what's making them go up and down. We use only x values to explain this. And that's important because a lot of students get this mixed up on a test and use the y values. So we use the x values to explain, that's not your bell either, when the graph is going up and when the graph is going down. I would recommend, and I'm going to do this with you in a second, you can write it down first. You're going to trace from the vertex to the x-axis. And that's going to split the x-axis or break the x-axis into two intervals. So we kind of trace straight down from the vertex, and that splits the x-axis. All right. To do the first problem, I'm just going to highlight the x-axis because this is really what we need to use, is the entire x-axis. And the x-axis is pointing to negative infinity on the left and positive infinity on the right. If I look at where my vertex is here, it's at the point 4, -3. So if we trace down to our x-axis, and you could draw a line there if you want to just trace, but that touches the x-axis at the number 4, which is the h value of our vertex. And we've split the x-axis into two pieces. Here's the left side, here's the right side. So which interval is the interval of increase and which is the interval of decrease? Well, on which side of the x-axis, and honestly, you could even just draw in the entire axis of symmetry if it helps you see it better. So we split essentially the graph into two pieces, but which side of the graph has the y values that are going down? Well, if you read the graph from left to right, which is important that you read from left to right, because it's easy to say I'm starting at the vertex and it's pointing up on both sides, so both of them are going up. But if you read the graph from left to right, it's a little bit different. Your very first point that you would hit is right here. So if you traced along this line, you'd be moving downward. And since that's moving down, that's going to be your interval of decrease. On the right side, once you hit your vertex and you pass over to the right side, you then would be moving upward. So that would be the interval showing where the y values are going back up. Okay, my pen is acting a little funny, so I don't know if I'm going to be able to write this right now, but I'm going to basically just circle the values on the x-axis that go with the decrease. So imagine this is going to keep going left forever, so it would be coming from negative infinity until you hit 4 on the x-axis. Once you hit 4, that's your vertex, you're basically going to stop going down and start going up. So if this is where we increase, then the increase starts once you're past 4 and you go up forever. And I'm just going to write this on here now that my pen is working. So there's our decrease, which goes with this interval. And that goes, and the way we're going to write this is the interval of decrease. So it goes from negative infinity till we get to 4. But I need to use a parenthesis here, not a bracket. The reason we don't use a bracket is because we're not going to include 4 in our decrease because 4 is our turning point. So you have to kind of imagine that you're, like if this is representing speed, as you get to a stop sign, you'd be slowing down, slowing down, slowing down. Then you're stopped. And then you start to go. When you're stopped at a stop sign, your speed is at 0. It's not decreasing and it's not increasing. So we use a parenthesis to show we're not including the 4 as a decrease or an increase. Then we start moving again and our speed would start to increase. So from 4 to infinity. And again, a parenthesis, not a bracket. So I want you to try the next two. You can pause this and try the next two on your own. And then you can push play. Okay. So again, if you have questions, you absolutely are welcome to raise your hand to ask for help. And if you don't have questions, you can start your homework, which is on the next page. Actually, before you start that, I think we can add to the summary. I did mention that that value that we're using right here is our H value. So you could write that your intervals are going to be negative infinity to H, and the other interval is going to be H to infinity. So we are using that H value. Okay, so on your homework, there's enough room for you to do this work right in your book. You do have to write small on the first 3 because look at everything you're asked to find. The vertex, the axis of symmetry, the max or min, the domain, and the range, and the intervals of increase and decrease of each of those functions. So just write small. The rest are won't take up as much room. So that's it for today.